Welcome back, CSCI 2021ers. This will be a makeup video to account for the Wednesday 3:35 session, which I will be unable to attend, and it will hopefully benefit those that attend class early in the day as well. Brief reminders to you that we will be discussing throughout this week linking and loading, and that will continue into Friday. That'll be our last content day, and moving our evaluations to that Friday since I'll be in class that day. Next Monday will be our last day of class. It's when assignment 5 is due, and we'll spend that period reviewing. Few sort of overview notes. We have discussed now this ability to separately compile code, and that the top level compilation here, number 1, compiles each C file on its own and creates a .o object file, versus compilation 2 will immediately convert all C files into object files in temporary space and mash them together to create this executable called main-func, whereas in the first compilation that's done explicitly as a last step. One of the great benefits of breaking this into 2 steps, as is mentioned, is that you can see error messages that are individual to each C file, but also if you save those .o object files and make changes to only single C files on a recompile, it's usually the case that all that needs to happen is to link those old object files to the newly created one. And typically, to save time, you would do this in the context of a makefile. So we ended last time with the following system discussion of how to speed this up. And it's generally by specifying that there are some targets in a makefile. There are some dependent files that need to exist in order for those targets to be accomplished. And then giving a command that once those dependencies are available, will create the target. So in the case of this main func, I need the object files present. In order to create the object files, I need the C files to be present, and then there are GCC commands in each case to produce those. Recall that this -C option will compile only, as in go from .c to .o, and the results of that compilation then are not a fully executable program yet, but they are an object file in this ELF format, executable and linkable format. Indeed, once you compile and have those .os, and once you link them together via another GCC invocation and call your main output file main funcs, that file will also follow this ELF file format, except instead of being linkable at this point, it is executable. It has a main in it and can be started running via the standard setup and run from the OS. To that end then, this makefile then, on detecting you've changed one C file, for instance only main func in this case, will only do this one recompilation and not the other sort of func01 if the .o is still up to date. And it'll do this by recognizing the timestamp differences. That if the C file is older than the .o, then no changes have been made to the C file that require an update of the .o. Versus if the C file is newer than the .o file, then I'll need to recompile that and then work my way up that chain to accomplish any targets that were dependent on things that have changed. In this case, just recompile. This pays the most dividends in large systems where, for instance, you have 20 C files, each containing some functions that are needed for the main executable. You make one change, for instance, to this C file number 8 and rebuild, then all that needs to happen is to recompile that one C function to create a new .o and then to relink this. And in the event that you attempt to make main func again, since nothing has changed in terms of the C functions in the source files, then nothing needs to be done in terms of rebuilding. So this is where we get some efficiency in terms of build times, which, if it's not apparent from based on our present projects in this class, will pay some dividends later on when you work on larger projects with hundreds of C files involved. It's time now to explore just a little bit more what's involved in these executable and linkable formats, these ELF files, as it were. And to do that, one of the first interesting spots to look at is how data is represented in it. In any C source file, where you would have, for instance, a global variable, like this R up here, that's comprised of 20,000 some elements, then it should be the case that the resulting .o that you would get from compiling this thing would have some storage of information associated with that global variable. Now, the folks who implemented this ELF format were no fools, and they decided to bake into the format itself some basic efficiencies. So what we're looking at here in bigdata.c is a rather large array of longs. It's 20,000 elements, the first few of which have been initialized to the numbers 1, 2, 3. Very similar setup on the right-hand side for big BSS. There's an array of longs, it's 20,000 long, but the initialization in this case with the open-close parenthesis just indicates initialize everything in here to zeros instead of putting the initial elements to 1, 2, 3. It's worthwhile to note that this 1, 2, 3 will be followed by a whole bunch of zeros, but the fact that the 1, 2, 3 is present there, it's going to make some difference. So all I need to do is to couple that with a little main routine and I could have a runnable program, but I'm most interested in looking at some facts associated with these two O files. Once I GCC and compile only the bigdata.c, I get an O file. Once I compile only this big BSS, I get another .o file. And if you use this handy little utility du, short for disk usage, and ask for how many bytes are in this file, we see a somewhat striking difference. As in this bigdata.o, with its initialization of 1, 2, 3, takes about 161 kilobytes. That's 161,000 some bytes. Versus the big BSS, it has only a single K, or about 1,300 some bytes. Now that is a marked difference of almost 100-fold in terms of storage. And despite the seeming similarity of these two functions, there must be a clear encoding difference between how they're stored in these compiled .o files instead. The explanation for this big size difference can come from an understanding of what's involved in the binary encoding of this form of the array, which has some initialized non-zero elements, versus this form of the array, which is of equal size but has all zeros in it. In fact, if you look at these two files and examine the ELF sections that's associated with them, what we'll find is that there's a different treatment of initialized to non-zero versus initialized to zero data structures in it. A handy utility for this, in case you've forgotten about it, is the readelf utility, command line program. Its intent is to make use of binary ELF files and print out various textual representations of them. You recall that this bigdata.o is in a binary format. It has a bunch of sections in it, and one of the things that you might want to do is just to look at what are the different sections and sizes of those sections that are present in there. And readelf with a capital S will do that. Running this command, you'll see on printed out before you some section information. There's quite a bit of it, so I have omitted those things that are not of any great import. Importantly, though, there's a .data section, which we described earlier as storing some sort of initial values in it. And present there is a series of digits associated with its size, as in 27100. Now, you'll notice then that the offset of the next section, which is stored immediately after it, this BSS section, it starts at this 27180. And that's accounting then for this data section starts at byte 80. It is 27100 bytes long, and that happens to be hexadecimal. And so then the next section, BSS, is exactly that quantity. Add those two together, that offset into this file. And there's a strong correlation then that this array of 20,000 elements, each element being a long, that's 8 bytes big, you expect that then to be about 160,000 bytes, and indeed the hexadecimal conversion of 27100 in hex to decimal gives us exactly that 160,000 bytes. So it will be a 160,000 bytes of a lot of nothing, but it'll be the case that the first few elements in this data array, which are what are present in this R, are those 1, 2, 3 followed by a whole bunch of zeros. But importantly, since I have some initial non-zero entries there, put it in the data section where you have these so-called initialized data. In contrast to that, compare this to the big BSS version in the big BSS.o, where the initialization wasn't really as refined as it was in that data version. Instead, I said just put all zeros in here. The BSS section, and why it's called that, I cannot say. May have learned it at some point, but I don't recall anymore. It was for data that should be initialized all zeros. And in looking at this data section in this big BSS.O, you'll see it takes almost no space, 0 bytes in fact. And so this BSS section starts at 80 and says I am 27100 bytes in hex big. That's another 160,000 bytes. But because the BSS section is implicitly filled with zeros, the very next session starts immediately after that, as in it's this other ELF section for comments. It's the case then that this thing takes almost no space in terms of the .o size, and explains why there is such a big difference in the overall disk space utilization of big BSS, which is relatively small, versus that big data .o version. In that the big data version has a very large sequence of bytes, that's the initialized array, versus in the BSS this long R is initialized just to zeros implicitly. There's no need to store all those zeros, just how many to put in when the program is loaded up. This results then in a significantly smaller file, which is nice in some ways and illustrates some of the ins and outs then of where the ELF file format takes liberties. The linker itself that's responsible for doing this mashing together of multiple .os has a tendency to need some main executable in order to actually produce an executable. But it's the case that you can do other things with this linker as well. That includes stuff like manually stitching together two .os to produce a new .o with the contents of both of them, which isn't itself yet an executable, but is instead waiting for a main in order to be created as well. Now, it's the case that GCC usually does this for you, as in there's very little reason in modern systems to issue commands directly to LD, which is the Linux linker. And the reason that it's called LD, which seems like it should be more associated with the loader, is that there is actually very little difference between the linker and the loader, and that they have to be very closely related to each other to get the job done. But as an example of this, you'll recall there's this little nm utility that if I have a compiled function and run this nm utility on it, it'll tell me what are the global symbols that are present in this .o file. One of them is in the text section. It's this func01. And the other global symbol that's present there is this put s, but according to the U here, it's undefined, as in not any place at this moment. It's used in here, but it is not actually defined any place. So that definition would have to be resolved before I could convert this thing into a full-on executable, in addition to providing a main. So if I have a second .o, this one with a func02 in it, it's possible to manually invoke by hand this little linker, LD, and with the right set of options, I can actually plug this .o and this other .o together so that what results from this is a new .o, this time named funcs12. You notice the familiar -o option here to control what the output name is. And in it then, if I run nm on it, are these two functions, func01 and func02, that came from the two constituent .o files. Now, this thing itself is not actually an executable, nor can it be without a definition and resolution of this put s and inclusion of a main function. And an attempt, for instance, to take these two and create an executable file out of it, you'll see that there's no ability here to sort of actually make that happen. The linker complains loudly about put s isn't defined. There's no start or main that's present. And that's the presence then of this -r option limits me to create a new linkable object, but one that is not executable. This should scare you away somewhat from manually invoking the linker, that in most cases GCC will do this for you, and you pass higher level options to say link various things like libraries into the executables that I want to do. But if you ever need to roll up your sleeves LD is a function like many others whose intent in life is to be to serve the goal of pushing together .o files to create other .os or executables. You just have to talk nicely enough to it in the right way to get the executables to pop out. GCC is good at that, so don't shy from using it in that fashion. There are a couple issues to resolve when you are actually pushing together and merging these .o files. And some of them can lead to common and persnickety programming errors. And so it's worthwhile to talk about that a little bit. So the linker, as it would stitch together multiple .os to create either a new .o or an executable or a library, it has to follow a few rules associated with symbol resolution. Now recall, symbols are generally identified as these sort of global type things, either a function name that is in the global scope, and in C that's really all we have, or global variable names. It's the case that there's a notion of strong and weak symbols that's present and used by the linker in some slightly odd ways. It's the case that if you have two strong definitions, that one of them is usually in conflict with the other one. But it's possible to have potentially many weak definitions for symbols that are then sort of fulfilled by a strong definition or maybe sort of resolved this way. We'll make this somewhat concrete in just a moment with an example. But the sort of main take-home here is that this applies mainly only to global stuff in C, as in variables outside of the scope of any function and function names themselves. Local variables are not at the level of a symbol in the sense of they don't show up as symbols in ELF files and can't be referred to from other C functions and .o files, so it won't create any problems. And this is then encouragement, as usual, to try to keep things as local as possible. Now, if you can possibly get away with keeping a variable in the local scope of a function or receiving it as a parameter rather than using it as a global variable, you'll avoid some of these linker problems, or at least limit the numbers of them that can hurt you. So here's our exercise, and it's associated with two C files because linking always involves separately compiling two C files and then merging, if the linking process, the resulting .o files together. You'll notice down here I'm going to issue this as a single GCC. Don't let that confuse you that it will be the case that this first xint.c file gets compiled to a .o, the second xlong.c file gets compiled to its own .o file, and then the linker will automatically be invoked to merge those two into a final executable. You can notice here there is a warning issued about this, but the main intent of this exercise is to try to predict, is it easy to tell when I run this thing what x and y values get printed out. You notice that x and y are first defined up here in xint.c as integers. They both have 0 values. There's someplace else defined this x to neg function. That happens to be over here in xlong.c. We'll get there in a second. But essentially all this main function does is call this x to neg function and then print out what is x and what is y. Possibilities then are that this function makes changes to the values for x and y, in which case I'd see different values here from the initial ones are, but if it doesn't make any changes to them, I should expect to see zeros over here. Looking over here then at the other C file where this function that's going to be made use of is present, you'll notice that a global variable is also in this scope. It's declared as a long, and it's also named x. And herein lies some of the trouble. In terms of these two C files on their own, nothing seems amiss. As in over here in xlong.c, I have a long version of x. I will issue some instructions in assembly that will change that x from whatever its current value is to -8. Over here in xint.c, I have a different definition for what x is, as in that it's an integer instead. Now, all of us at this point in the class have spent some time on assembly instructions, and you know there is danger wherein you have a write which would change some value in memory from its integer equivalent to some other value, versus there's a separate assembly instruction that will change longs from some value to a different value. And this have to do with, for instance, the move instruction to move a value into a memory location. you always have to say how many bytes am I moving. And this corresponded then to the integral types for x in int over here, that'll be move L, versus an x over here, which will be a long value, which is 8 bytes instead. To that end, if I pick the wrong quantity of bytes to change, there can be some dire consequences. And indeed, what you see in this case is that there's some confusion about it. That the long over here is what's considered a weak symbol. And this is on account of it being uninitialized. This is a sort of half-baked rule that is present in the linker, and so it is the case that the linker is going to wait for a further specification of what that variable is actually going to be. And it finds it as a stronger definition in xint.c. It's over here with an initial value, and that to some extent then takes precedence over the long definition up here. That will then be used as a 4-byte memory unit so that x has 4 bytes associated with it, despite this other C file having a notion that it should have 8 bytes. Now, the important mismatch then comes as I would change x to -8. For some reason, I will see a change in y as well, that it ends up being -1. Now, the only real way to understand this is to backtrack and sort of understand that x and y are most likely stored in the global area memory, and they're stored adjacent to each other. That means if I write too many bytes to x's location, I end up clobbering the value for y. Under normal circumstances, in sort of terms of x using this code, I'd see this function will change x to -8, and then as I print over here, I expect to see -8 for x and 0 for y. But since this change to x is going to actually assume it's 8 bytes long, based on the definition of x in this xlong file, it's going to write 8 bytes to wherever x is located. It happens to be in this adjacent file where it's given only 4 bytes. So the write of 8 bytes to x's location ends up overwriting the area, getting into y's area instead, and slamming a bunch of 1s in there. As -8 is a negative value, we'll have a whole bunch of leading 1s associated with it in a 2's complement representation, and that will leave all 1s in y's area of memory. That's what makes it look then like -1. So our end message here then is pay careful attention to linker warnings if you get them. And if possible, avoid using global variables. They can create difficulty in linking, and it can be oftentimes hard to track down exactly what's going on there unless you have very careful eyes and are sensitive to this kind of obtuse warning. But then you already knew that having global variables is potentially going to lead to trouble, not the least of which is in linking, but also in program design and enabling concurrency and lots of other sorts of problems. Now, it is the case that eventually you're going to have some global stuff at stake. So this is where the value of header files come in. And typically what you'll see in header files is a declaration of the types of various things. Oftentimes, if there is an actual global piece of data, what you'll see in the header file is a declaration that this is external to any of the files that are including the header. As in, the modifier extern here says there is going to be an x and it is going to be a long. And anybody who includes it can rely upon it being there because I promise eventually to link you to some .o that actually has this x with 8 bytes of storage in it. And there will be a function named x to neg8 present out there. The typical approach then in your C files is you #include this header file, which will insert this bit of code at the top and say, yes, there's going to be a function, and yes, there's going to be a value called x that's 8 bytes long. If it happens to be the function, or the C file, where those two things are defined, there's just a little bit of redundancy, but you then at least are able to verify that everyone else thinks this is going to be a long, and indeed my definition for x is going to be long as well. You'll most likely get linker errors if this int or this long is changed to an int and disagrees with the actual definition of x here. Whereas in other files where I'm not actually going to declare these things, then I'll just #include this thing, which is a promise that if I have a main function that's going to make use of this function and this variable, it will have the appropriate sizes associated with it. So proper use of headers then gets you, to some extent, a better error message than if in my xmain.c I include the header and then immediately include another definition for x which disagrees in terms of its size, or even a redundant definition. Then what you'll get on attempt to compile is that you have a conflicting types error. That x is declared previously in this .h to be a long and presently here in this C file to be an int. You should really resolve those things before proceeding. So without using the header files, there's no ability for the compiler to coordinate these definitions for x's in various spots between the different C files there. And the linker barely has a fighting chance then to get it right. With the use of header files, we can enforce some sort of discipline in terms of what are the sizes and types of the various things that are going to be shared amongst these different programs. So then, that leads us to the immense journey that a program must go on from its humble roots as a .c text file to eventually become a running program. The apologies to Lauren Isley is that he has a book called The Immense Journey, which is actually about the natural world. A bunch of fantastic essays, well worth a read. But for our present moment, let us consider the journey that this C program has to go on after you actually sit down and write it in your favorite text editor. The first stage, generally referred to as compilation, is a combination of a bunch of internal steps in which GCC will typically pre-process this .c file, create some internal representation for it, a big tree-like data structure with some sequencing in it, optimize it, as we've seen the optimizing compiler can do, to potentially rearrange those operations or expand upon them in an attempt to make the ultimate assembly code that's produced somewhat more efficient. And this then being a late stage in compilation of assembly generation. You can stop it here with the -s option and actually look at what those .s files comprise, and they'll still be textual and contain things like move queues and add Ls and idivs and so forth. But typically this rigmarole doesn't stop there, that instead GCC will call its compatriot GAS, the GNU assembler, to take the .s files that it is storing temporarily in most cases and assemble them into binary .o files. These are in that ELF file format, and typically you have one .o file per .c file that is produced. That's what enables you to do things like a separate compilation of multiple different C files and then detection that only one of those C files has changed, so I only need to recreate a single .o file. After getting those .o files in hand, the linker, LD, is invoked to take a whole bunch of those, mash them together, rearranging and combining their text sections, their data sections, so that the resulting ELF file only has a single text section, only has a single data section, only has a single BSS section, and in some cases then can actually be executable. It's also the case then at this stage, if there are any libraries that are requested to be stackly linked, their definitions will be copied in and merged along with text and data that's already present from your C files. And there'll also be notes made on if there's a so-called dynamic library that's dependent, something we'll talk about later, then make a note of that so that when the program is actually loaded up, it can be sort of linked in there. Now the result then of linking is a stored program, as in sitting on your disk someplace is some program file. Maybe it's a.out, maybe it's program.out or prog.out. It's in the ELF file format, but it's a slightly different version of the ELF file format in that it is actually executable and you can run it. But at this stage, it's just sitting there, and in order to get it to do anything, you'll have to continue that chain of events. There's another entity that's tied up with the linker and stored programs called the loader, and its job is essentially to take this disk image of a program and to plop it down someplace in memory such that the operating system can actually schedule it to start running instructions associated with it. The process there goes something like mapping a bunch of pages in memory so that the .data section, the .text section, and the .bss section are all initialized someplace, that if there are any dynamic libraries present, that more pages of memory are mapped so that the system-wide definitions for things like printf and malloc and so forth are linked to this thing. And finally, to set on the OS deciding it's time for this thing to run, to set the instruction pointer for the processor to be the first instruction of this program. At that point, this thing is a schedulable, runnable entity, and the OS will take care of giving it a slice of time to run for a while, putting it to sleep for a while, and then rerunning it if there's still more to do. This includes things like checking for exit conditions, and if it goes out of bounds in terms of its memory map, killing it, usually with a signal. This is stuff that will be discussed more in an operating systems class if you go down the line. But just getting to that stage involves a few other things that we haven't yet talked about. For instance, this loader, and maybe a few other facets of the linker. So that will take us forwards to the next bit of discussion. But this is a long and somewhat involved process with separate and different tools that are distinct to each stage. It's the case that GCC itself is really a wrapper over a bunch of internal steps, and those include things like pre-processing, optimization, assembling, and the linking at compile time. But there are problems that can arise at any one of these steps and later on, that after having stored your program and attempting to run it, there's some additional things here that can go wrong that deserve some mention. So for the moment then, let us consider these two notions of linking. We've alluded to the fact that there's one that will merge a bunch of .o files together. And this is generally touted as traditional static linking, as in when I have a bunch of .o files, I can merge them together. And all of the global symbols, functions, global variables, and so forth, they'll get merged into individual sections. At the point that you have a completely static executable, the loader will copy this into memory, set the RIP so that things can get going, and then the program itself will move forwards doing work in terms of modifying its memory image, talking to the user, accepting text, modifying files, etc. It is the case that there's an alternative to this, though, that we've alluded to, that allows you to share definitions for various libraries. It's tied up in this phenomenon called dynamic linking. Now, it's the case that at compile time, the linker will merge a bunch of .o files together and create an executable. But it's the case for this, when you have dynamic linking available, you don't need to commit to definitions for everything at this stage. That there can be some definitions, such as the notion of what does printf do and what does malloc do. These can be left undefined, oftentimes represented as big U symbols when you ask what are the global symbols in this executable. The loader still has the same basic job to set up the part of the program that is stored on disk, to copy that into main memory and set the RIP. But it also has the responsibility of any dynamic definitions that were not specified at compile time but need to be available at runtime. They should be linked in. And this is typically called then dynamic linking. The approach that we'll discuss for this is associated with looking on the system to say, is anybody currently using this library that has printf in it, the C library? If so, there's already a copy of it in main memory someplace, and for this new running program, all I have to do is map some page of memory for that thing to this printf definition, and all should be hunky-dory. This is a somewhat more involved process and is newer. It has some advantages and disadvantages that we'll discuss. But generally then, the code for a running program is spread all across memory and in the shared libraries that it makes use of. So the accounting issue of how much running memory is this program actually using becomes a little bit harder to pin down, because if there are 30 programs and each of them is sharing printf, do you charge that printf to all of them or to none of them? So long as at least one program is using printf in the C library, there's going to be some memory associated with it, but it will be much less than each program having its own copy of printf. So a GCC by default will do dynamic linking, and this is the more modern, sort of more sophisticated way to do things. You can change this though, and by passing the -static option to GCC at the command line, you'll get a completely statically linked executable instead. And so let us consider that difference with this simple hello world program. You'll recall cat will take the contents of this .c file and just print it on the screen. So in terms of compilation then, the first way I'll do this is to say GCC, name my output file hello dynamic, and pass no other special options to GCC, so it'll do its default thing. In the second compilation here, where I'll call the output file hello static, I'll use the same .c file, but then in this case use the --static option. Now, if you examine the file types associated with these two things, you'll see something interesting, that they definitely have a different file type, as in they're both ELF files, but in the first case of this hello static, that was the second one we compiled here, the static compilation leads to a clear designation that this thing is statically linked. Versus the file type for hello dynamic is also an ELF file, but there's explicit mention here that is dynamically linked. And there's this LD Linux business that's tied up within it. This is the so-called dynamic loader, the thing that will be responsible for taking this particular executable, moving it into memory, and ensuring that any of the dynamic libraries that it needs are actually linked to it as it gets running. To that end, this is an interesting thing to consider, again, in terms of file sizes. As in, if I compile these two things as I did before, the first dynamic, which is the default for GCC, the second static, which I must request explicitly via the --static option, and then again use this handy little utility du, tell me what are the sizes of all the hello files in here, you'll see that, oh, this hello dynamic is significantly smaller in terms of its byte count, about 9K versus 72K big for this hello static. An immediate question is, why? Why should there be a big size difference between these two? If the answer isn't obvious, you'll have to recall back that our point in terms of static linking was to ensure that this executable has in it everything that it needs to get going. And it was the case that if you look at the source file here, the printf function was indeed needed. And anything that printf uses under the hood, and there are quite a few things actually that it makes use of, those also have to be incorporated into the executable. This isn't by virtue of me writing a lot here, but it is by virtue of me making use of this printf function, which is part of the standard C library. If that is to be included in this executable, then the definition for printf and any supporting functions have to be copied into this static executable. You can see that that takes a significant amount of space, 60,000 some bytes, maybe 63,000 or so, if we're being specific. Versus the dynamic executable will not have definitions for those things, printf. Instead, I'll have a big fat U undefined for printf that's present in hello dynamic. And to that end, I'll save myself a whole heap of space by not including parts of the C standard library, on the assumption that when this program starts running, it'll be available, made available to me by the operating system. So then you can look specifically then within hello static, and you will see defined in there a strong symbol for main, a weak symbol for put s, and this was essentially what is translated to the what a standard printf is. As in, if you're printing just a string, that gets translated down at the compile level to a put s, as in put a string on the screen. Instead, in this dynamic executable, you see a strong symbol for main, as in that was part of the C that I wrote, versus you'll see a big fat U for this put s, which is what printf eventually will compile to. The U here means undefined, and it is just so, that the compiled version of this dynamic one does not have a definition for put s. Instead, the intention is to link it at runtime, so that this is something that the operating system is going to have to provide as the program gets up and running. So that main difference then translates to a size difference here, and it's the case then that you can see there's quite a bit of space overhead associated with including the C library in there. I may have misspoke with this is actually 721,000, so that's like a 100-fold increase or so in size for the static version. The main advantage of static compilation is that this thing is fairly self-contained, so barring some other concerns, like I have the same processor as you could send me the executable, and I could probably run it on my system if they were both Linuxes that had an Intel chip. Versus if you send me this dynamic executable, there are some gotchas there. I may have a slightly different set of dynamically linked libraries on my system, which would not make it possible for me to run this executable. So that's the stage at which we'll leave off for the moment. There are a bunch of issues associated with dynamic linking and loading that we'll cover in a hurry on Friday, but this should give you somewhat of a primer to understand what's going on in lab this week and also what will happen to close us out in terms of course material. To talk a little bit further about these dynamic linking issues that are at stake, in particular, we'll focus a little bit of attention on this LDD utility, which can tell you which dynamic libraries are needed by an executable. So, until Friday, enjoy and code hard.